I'm Vladimir Spokoiny, and WIAS is a WIAS Institute in Berlin, and I'm head of a research group. And what I'm going to present here is an ongoing project. We are only recently started this project. I show some of results we obtained so far. But from the other side, this project is a continuation of a long-term research, and there is also some theory available, and this is probably a good point that we try to combine theoretical study and empirical research together, and particularly try to show that the good mathematics could be useful in financial applications. Okay, so the talk is, so the title is a little bit specified relative to the program. So we are interested in the modeling of high-frequency financial data, and particularly in monitoring and forecasting. So here's the outline, and I will give some motivation and show some procedure and some theory to this procedure and some empirical results. So starting from the motivation. So this is a part of the data, high-frequency data. So what you see here are so some stock at the New York Stock Exchange, 2001. This is 2nd of I guess 2nd of January, and what you see here, so this is the time during the day, and what you see here are the prices of the stock, and the vertical lines are the volumes. Okay, so you can see from this immediately the data is not simple, and actually there is a lot of more information available. I don't show this, but so here some components of this data which could be interesting for financial applications. So this is what you see here is the price itself. So you see some dynamics, daily dynamics in the price. This is bottom line. So what you see here is these are the returns related to this price as log returns. This log of ratio of two neighbor prices, and what you can see from here, and what is interesting here is standard deviation or the variability of these returns, which is called volatility, and it is important information for the market. And the next is intervals between trades. And this is something like intensity of the trading, and also important information. And this last line are the volumes, which are traded at every time point. And what you would like to do, you would like to have some parsimonious model which allows to monitor and to model this data, possibly to predict, and then to optimize the trading strategy. So this is some stylized facts of this data. So what you can see immediately, there is a clear inhomogeneity in the data. It doesn't look really homogeneous in time, especially you can see here. So you have some clusters of high intensity, small intensity. You can see different. So if you do it day by day, you also realize there is a daily inhomogeneity. In different days, this looks differently. So what you can see also, there is some dependence. So I mean, when the price goes down, the volatility goes up, and so on. So the components are clearly correlated. And if you have some big volume once traded, after that you can observe increased intensity of trades in the same stock, and so on. So, and another types of the data have different nature, different scale, and different presentation. So the data are different. So it's not like just for process signal plus noise. It's really a really special structure for every process. So the aims are, so as said, monitoring, modeling, forecasting, and particularly important is to put the available information together, to profit from observing multiple information, analyzing different components together. And exactly this is the topic for the future projects. I don't show you today any result in this direction, but we have some, but it's not yet. Sorry, I forgot to say this is an ongoing project, and there are some of my colleagues involved. Particularly, we cooperate with Nikolaus Halich from the Humboldt-University, and so the results I show today are partly by my PhD student Enzo Giacomini and Mstislav Vladimir. So. Now what we apply here basically is called local parametric modeling, and this I am going to explain in details. So what is a local parametric approach? So first of all, we try to use for every component of the data. So YT now is any of component of the data. It could be anything. It could be stock price, it could be returns or volumes or interval between trades. So basically what we assume, each time this variable is a random variable in conditional distribution. Conditional distribution of this variable given the whole past. So I consider the time discrete, and the time step is just 1. And this is the mean conditional distribution given the past, and this guy is from some particular parametric family. And the parameter which drives the distribution of y is denoted by ft, and this ft is a random process by itself, but in this case it is predictable random process. So this is a non-parametric assumption, very general. Basically, you can put almost everything in this framework, as this is definitely fulfilled for all the process we consider. But if we want to model, we need to specify the structure. And now the structure of the whole process y can be given via this driving parameter ft. And basically what we assume here, and this is called local parametric assumption, is that for every time point t, there is a historical time interval, where we have only historical data, in which this function ft is specified by one parameter theta. And then ft is basically the function f theta of xt, where xt is something like explanatory process which could involve particular select value of y. Xt is information which is important for the distribution of y. So xt is a predictable process, and what we basically say is the distribution of yt given the past is determined by the state of the process xt and the parameter theta. Xt is what you observe, and theta is an unknown parameter. So in this sense, if you would know theta, you know everything. You know the conditional distribution of the process y given the past. Okay? So, but theta is something which you don't know, and then what you can do, you can identify this interval I and estimate the parameter theta using the well-known technique from parametric statistics. Particularly, you can apply the maximum likelihood estimator and maximize the corresponding log likelihood, which is written here. You can write down the log likelihood very easily. And so if you estimate the parameter theta, again, you know f, you know the distribution of y. And then you can do it step by step, and then you have the tools for modeling and also for prediction of the process y by this procedure. Okay. Now the point is so what I'm going to explain is essential point of this construction. Essential point is here is this interval I. And we will see that this is the central part of the whole story. So what is the meaning of this interval I? So if we go back to our data, so this interval I would mean the interval in which our process is simply organized, what we call interval of homogeneity. So, and the idea is, so what you can do basically, there are two strategies, and one strategy is we build some complicated parametric model, which can probably drive the whole of your dynamics. It could be, I don't know, stochastic volatility, or Garch with P on Q large, or Arch with a large P, and so on. Then you have a rather general model which can probably model a lot of things, but this model involves many parameters. And so you need some time to estimate all of these parameters. And therefore, you have one model, but this model could be difficult to calibrate. You need time. And therefore, if something happens on the market, if you have a structural change on the market, so you need a relatively long time to recalibrate your model, to re-estimate the parameter and so on. And our idea is to say, instead of using a complicated model, what we are doing, we say, you can also use a simple model. Simple model, so if you look at the prices, what could be simple model? That the price is constant or price is linear. So you have very clear trend in the price. And then what you can say here, okay, this in the whole time scale, the price is not constant, is not linear. The same volatility is not constant over time. But for every time point, you can find in some interval, say if you are here, you can go back for this time interval. In this interval, I think you can approximate the price more or less by a linear function. Or for this interval, you can approximate the volatility by a constant. And this is the idea. You use a very simple model, but this simple model cannot be used to model for a long time. But it can be used adaptively in the sense, so you can adjust for simple model time interval in which it applies. This is the idea. And what is the advantage of a simple model? Now you are because simple model requires only few observations to estimate or to calibrate. And therefore you are very flexible. If you re-estimate, recalibrate your model during the time, you are very flexible to any kind of changes on the market. Okay, now the question is, the most critical question is, okay, here, how we can define this interval of homogeneity? So I recall our non-parametric assumption is that Yt is given by the distribution derived by Ft. Now our parametric assumption is that Ft comes from some parametric family. Now the question is, what means that this is not precisely fulfilled? The question is how we can measure the modeling bias. What is the payment for the use of the wrong model? So what we are doing, we definitely use a wrong model. The life is much more complicated than any parametric assumption. But we use the wrong model, we approximate f by f theta, and we can measure this guy by the accumulated Kullback-Leibler divergence. So what you see here, this is a Kullback-Leibler divergence between the distribution of y given ft and the true distribution fc of theta is the distribution which we use for our approximation. We sum up this guy over the time interval capital I, and our small modeling bias condition basically means that this capital delta I of theta is sufficiently small for some value of theta. So this means this accumulated Kullback-Leibler is small within the interval capital I. Then this approximation ft by f theta of xt is a good one. This is a...
Other situation when it is big?
Of course. If you take a long interval and use constant approximation, it is accumulated. So for every time, so if you have not, for one single observation, there is no normalization here. For one single observation, if you have big difference between these two distributions, you have already one term which contributes a lot. And you sum up over interval. For high frequency data, you have a lot of summands here. It could be bounded only if this approximation is really good.
For example, a single function that has infinitely many
yeah, for
near zero, and now you would like to approximate the bias. I think then
yeah, so
that's arbitrarily big, right?
this could be big, but then this sign function could be a kind of noise. And you approximate again by a constant.
Everything that we don't put into the bias, we put into the noise. Is this the answer?
Not really, but we're looking at some systematic. Okay, now basically this is a justification for everything what we are using in our theory. There is some result which actually is known as a theoretic information bound, and this result basically tells, so if you have this capital delta I bounded, I recall this guy is actually random, because this is random and this is random as well. So this is a random quantity. But if this random quantity is bounded in mean by some value capital delta, then everything what you can establish for the parametric model, all the bounds for the risk, etc., and for the loss, can be translated in the original model by some change of the loss function. If you have zeta losses under the parametric model, then you have log zeta losses under the real model, but still you have stochastic bound for this guy. So this means basically if you can compute your trading strategy under the parametric measure, doesn't matter, Black-Scholes, Bates, or Heston, or what you like, Vesicek. So if you have bounds for this, and then you go back to the real life, real world. So you basically change your loss function a little bit, and you pay in the risk additional value capital delta, which is this modeling bias. If modeling bias is small enough, then basically you have the same bound for the losses under the true measure, if you checked it under the parametric one. Particularly if you consider the losses, field likelihood, then you have this bound here. I don't. I don't explain this because I don't introduce this fitted likelihood. This bound gives you a natural rise to the question: what is the oracle interval? What is the optimal interval of homogeneity you can consider? So basically, oracle interval, the best choice of the historical time interval is that you consider this quantity modeling bias, and if it is bounded in mean by capital delta, then you have a reasonable quality approximation, and what only you have to fix to this definition is this value capital delta, say 1. And then you can define the oracle interval, and now oracle is oracle because it depends on the unknown distribution f. If you want to do a real monitoring, real inference, you have to mimic this oracle. You have to implement something which compensates for this unknown distribution. And this is exactly the procedure I'm going to present here. And the idea of this local change point selection procedure is to select the largest possible time interval of homogeneity, capital I, by testing a parametric hypothesis that our model is exactly parametric against the change point alternative. What means this hypothesis? Say this hypothesis means the price is constant or linear, or volatility is constant, or intensity of trading is constant, and this simple hypothesis to test we need an alternative, and change point alternative means that that we test against the structural change in the process. Y change point is, so what change point basically means you can split the interval into two intervals. I will show a picture just in a minute. And within this interval, you have again the same parametric structure. This means you work all the time with the same parametric structure but for different intervals. And the change point approach delivers some additional interesting information. So now how we test the hypothesis. And this is the central point of the procedure. So what we want to test for some interval capital I, we will want to test the hypothesis that f theta, the process f, is homogeneous with the parameter theta. And this leads to the likelihood, I wrote it already, there is a likelihood under theta for this parametric hypothesis. And likelihood ratio test, sorry, it's not the likelihood ratio test based on the so-called fitted log likelihood when we maximize this expression with respect to theta. So we define the maximum likelihood estimator as maximizer of this, and L hat is the maximum of this likelihood with respect to theta. And now the change point alternative is given here. It's very simple. You just split the interval at some point tau inside this interval into two subintervals, which are called J and J complement. You compute the same likelihood structure for J and J complement. The only difference is within G you have parameter theta 1, and within J complement you have parameter theta 2. And the likelihood ratio test is just take the difference likelihood under the alternative minus likelihood under the null. Under alternative, you have sum of two different likelihood for J and J complement, and you subtract J, and this is the test statistic which is written here. And so the idea is to say the interval I is homogeneous if this guy is not too big. Okay, this is a graphical illustration of this likelihood ratio test. And so you have the interval capital I, and this is J complement, this is J, and this is point tau. And basically, this was the test with given location tau. And what we are now doing, we don't know where location tau is. We shift it within some internal subinterval script tau within this interval capital I. So
you basically assume that, very faithfully that alternative has only one change point.
Exactly.
In other words, that your parametric family, just one change point would be enough to describe deviations from the.
Yeah, this is a very important point. Thank you for asking. So indeed, we assume exactly one change point, but this is the meaning of the procedure. I show you in the moment why we stick with just one change point. No, we don't assume, but we check for one change point. And the idea is because we start from very small interval and increase until we see some difference. And therefore, because we successfully increase, so we go from homogeneity to just some change, which can be indicated by one change point.
You explain it differently to me. I think you give the wrong answer here.
Of course.
The way I understand it, right? The simplest way to check non-homogeneity. So what is the simplest alternative to homogeneous situation, as he always says? The change point. That could also be a linear deviation. It could be a parabolic deviation. But he's just using the simplest form. That's why I don't understand why you answer, I assume. I mean, for you, this is just a procedure to test against a certain simple alternative. You can take another more complicated
So the simplest way you check, isn't it your assumption too?
Yes.
It's not an assumption. It's not an assumption. It's a way to check things.
No, maybe I show in a second how it works, and maybe this will clarify the story. So this is the whole procedure. So you have the time point capital T where we are. It's now. Now we want to find the interval of homogeneity. It's historical interval, and we go to the past with different steps. So it is M1, M2, T minus M1, T minus M2, and so on until T minus Mk. And then we successfully check in this subinterval here on the change point. So at every step we check some next subinterval whether there is a change point here. So we start here, then take the next interval, next, and each time we test this interval. This is the last interval we are checking on a change point, and this is the idea. And each time we apply the same test statistic. And if all this test does not indicate any change point, we accept this interval, the next interval. Okay, now, yeah.
So I have to understand that the criteria for selecting or splitting the interval depends on just the change point.
On the test statistic about the presence of change point. So this is a procedure in formal way. So you have at each time, at each step, the interval script tau k of this form. And for this interval, we compute the corresponding test statistic, which is this change point test statistic, whether there is a change point in this particular interval. And if this guy is not larger than the critical value z, then we accept the interval. Otherwise, we reject it, so we will have to stop. And then we use the latest interval, which is screened without change points. This is the idea. And maybe now I show how it works online. So it will come. Okay, so this is the illustration of how it works. So the driving process is something like hidden Markov chain process, and this process, this is the true data, and this step line is the value of the parameter, and the parameter jumps between 5 values when this circle becomes a point at random new step. So what you see here, it will come. So what you see here, these red points are the critical values. And the test statistics is what we are checking for every interval, historical interval, we estimate at this point. This is really monitoring, and this is our past data. And what we want to indicate where there is the interval of homogeneity. This indicated interval is shown here, and this you see test statistics. So when the test statistics jump above the critical value, we indicate this means we found a change point. And then what you see here, basically, if the process jumped, so we need some time to train this. And you see here, now it is trained, we started to indicate the change point. So you see there are some delay. And maybe what is interesting here, these two green lines are actually the Oracle confidence set. There is a confidence set around the true value. And our estimate is almost all the time within this confidence band. This means we really provide the Oracle quality. This means our estimate provides the optimal what can be done in this situation. All the time we give the state of the process, which is really on the market. And this model is actually very good because later we plan to use exactly this model for modeling the. It is a simulator, for example. Okay, so now I go back to my talk. So this is the procedure. what is interesting for this procedure, also important for this procedure, so this procedure has some parameters. And these parameters are the critical value. I recall these are red points. And you can imagine how important it is to fix these red points in the right way. This is your sensitivity to the changes on the market. And so important part of our procedure is that we can fix this critical value, and the idea is the procedure is nothing but multiple testing procedure. You are doing multiple testing on change point. And in the hypothesis testing theory, you have a way of fixing the critical value just to check that the first kind error probability. And we have analog of this condition in the testing setup, and this analog is called propagation condition. This means we consider the homogeneous situation. In the homogeneous situation with no jumps, we know what should happen. We should not reject the hypothesis of homogeneity. And this is what we exactly check by our procedure, that the rejection of a correct time interval happens not too often. I don't go into the detail, but this is quite straightforward, and we have complete theory for this. This means that the theory is derived exactly for the critical values computed by Monte Carlo under this condition. So for the case of local constant modeling, volatility or whatever, prices, intensity, volumes, the procedure becomes especially simple and straightforward. It's very, very easy to implement, very easy. So it can be rewritten in terms of Kullback-Leibler, and the estimate is a mean. So it's really fast. So you can do it online. And this is another advantage of use of simple model. You can very easy compute, estimate, and calibrate this model. Okay, so this is the critical values which you have already seen, so how they depend. So what we can say by the theory is, so I recall there is a notion of oracle, and the theory basically tells that we really mimic the oracle. The resultant quality of estimation is due to the oracle quality, and this result is stated here. And there's a propagation property, and its stability, and this is the oracle bound. Maybe I show this result only for the local constant case because it's more illustrative. Yeah, this oracle bound in the local constant case. Basically, the result tells that the distance between the oracle estimate, this estimate when you, so here this procedure is ideal, oracle procedure. Oracle, the God tell you which interval you should to apply, interval of homogeneity. You know this, and you build this estimate. Theta tilde k star is the index for the optimal interval. And theta hat is our adaptive procedure computed from the interval selected adaptively from our procedure. And the distance between these two guys, Kullback-Leibler distance, is more or less quadratic, and quadratic difference between these two guys is multiplied by the sample size corresponding to the oracle estimator is stochastically bounded. This means root n consistency, where n is the size of the oracle interval. Good. So Wolfgang, it's the applications.
Oh, it's a different data set. It's a different data set.
Yes.
So it's not the application you showed us before. It looks very similar.
So answer. You heard about this? So there's a different data set. The same plot.
Well, it says EIG, and there it says IBM, so what's the difference?
So it's
Or the title is different. What is the
okay.
data?
Okay. So another important point of this procedure is, so this is one procedure. You have almost nothing to change to analyzing different components of the market data. So we have, so here, this is the prices for different days. And this is the real price, this is estimated. Each time, I recall, we estimate using only historical data. We don't use the future data for estimating because we are really interested in monitoring. So each time estimated at this standpoint is something which used only historical information. And you see here that our estimator captures the changes of the process very. So unfortunately, I cannot draw the line here, but if you see, so here almost no delay. It's very small delay in detecting the change here. And this is quite remarkable, and the same is here. Even small changes are indicated quite easily. This is
Which data set this is? Is it AIG or IBM? What is it now?
I think it's still IBM.
So it was always IBM. So the title was wrong in the first picture.
So it's a question to answer.
The beginning was another data set, now it's IBM.
Now it's IBM.
Across 1 week, the beginning was 1 day.
Okay, this is the same for volatility. Again, the procedure, only what you have to change in the procedure is the formula for Kullback-Leibler, because for prices you have signal plus noise model. For volatility, it's the parameter is the variance of the data, you can see here. So this is the estimator of the volatility. You have, sometimes you have jumps, and these jumps, if you observe the whole data set, you probably would not jump here. But we are monitoring, we hear single big return, and the market reacts a little bit, and then goes very fastly down. This is an indication of good reaction. If you would not do it adaptively, you have a rather big peak here, and so on. So the same story here. So this is the estimate of volatility, and you observe the results are not homogeneous. This means at every point we estimate from historical data, and the result is not local constant.
This is just re-explaining the data. So what do I do with it when
I am almost done.
Oh, but this is just re-explaining the data.
If you want, but you can of course. So we this is only monitoring. So this is only the indication something goes on the market or not. But you can do a short-term forecast from the models, from the latest estimated model. And the same is for trading intensity, is something like exponential model, as was explained, and you see here clear inhomogeneity for different days. This is daily inhomogeneity. There's 4 sequential days. The pictures are quite different, and this is the estimated result. And you see here, so we try to capture the change in intensity of trades more or less online. And this is the same for volumes. Again, you see a similar picture all the time. And now is probably my last slide I would like to explain is the direction where we want to go. And this picture goes back to my simulated result, which I showed you before with this hidden Markov chain. So the idea is, okay, something changes on the market. If you are not trained, you need some time so you indicated some change. If you are not trained, you need some time to train you, to adjust your trading strategy. What we are going to do is to make something like hidden Markov chain behind our system, and the change is the market change from one state to another. This is exactly what I showed in my simulated example. I'll show it in a bit. And the idea is there is some hidden Markov chain behind the situation on the market. And what is going on, you just jump from one state to another. And if you are trained for all your states, you only need to indicate when the jump occurred and what is the new state. And then you are already trained for this new situation. And this is what you see here is a kernel density estimation of the estimated results. So you see here, this is the estimated values. So what you are looking at is how much time the process spent at every point.
I'm confused by the TI.
TI.
Why not PT?
Yeah, VTI is the volume trade at the point TI.
Okay, so intraday TI.
Intraday TI. It's another TI. Okay, so what you see here, the process spent a lot of time here, a lot of time here, a smaller time here. You have three clear peaks. What you can say is there are three states, 1 to 3, and the process jumps from one state to another. You train for the states, you say to the trader on the market, and so if he knows in which state he is, he will change that, adjust the strategy to this. And using this hidden Markov chain, you can, of course, solve. If you have this mechanism, is already a global mechanism, and you can optimize the trading strategy using this stochastic machinery for hidden Markov chain. And I think I stop at this point. We have some application to daily data, and we did a comparison for risk management on the basis of the daily data, but it's not the topic of what I'm going to discuss today. And there are some literature where you can find the description of this procedure, and one item is missing here. All of this is in my forthcoming monography where the procedure is explained in the details, and maybe for the time you ask me the question, I put it running.